Hi everyone, welcome to Lab 5 for Physics 2212. The purpose of this experiment, let's take a look at our introduction here. The purpose of this experiment was to observe and collect data on the behavior of a magnet falling through a conductive aluminum foil tube. We then created a computational media to simulate the interaction between the magnet and the tube. Finally, we compared the results of our experiment with the predictions from a computational model to analyze any discrepancies. So let's take a look at the main results we have here. The experimental time measured from when the magnet entered the tube to when it exited was 1.456 seconds, while the computationally predicted time was around 1.97 seconds. This gave us a percent difference of approximately 30%. Now let's take a look at some of the fundamental principles. This experiment relies on three key principles. First, Faraday's law and Lenz's law. These explain how nature resists change in magnetic flux by generating an induced current that creates a magnetic force opposing this change. The induced EMF is directly proportional to the rate of change of magnetic flux. Second, the Biot-Savart law, which allows us to calculate the magnetic field generated by the induced current. And finally, Newton's second law, F equals ma, which we use to compute the gravitational force acting on the magnet as it falls. Let's take a look at some of the assumptions. There were a few assumptions made during this experiment. We assumed that the bar magnet could be treated as a magnetic dipole, and additionally, air resistance was considered negligible, meaning the only forces acting on the magnet were gravitational and magnetic forces. So let's take a look at some of our model here. In this setup, the system was defined by the aluminum foil tube and the magnet, while the surroundings including everything else. Initially, the magnet was at rest with zero velocity and had no magnetic force acting on it. So here's what we did in our experiment. First, we assigned the north pole to the magnet using a magnetometer app. Next, we dropped the magnet through the aluminum foil and recorded the time it took to pass through. We repeated this process 5 times to improve accuracy and calculated the average time to be 1.456 seconds. The results showed that the magnet fell slower in the tube compared to free space due to an upward magnetic force created by an induced current. So here's some of the glow script code as mentioned here. Um, Now let's take a look at the model output, right? Uh, in the computational model, we define key constants such as the mass of the magnet and its magnetic dipole moment, as well as the tube's dimensions. The model treated the aluminum tube as a stack of rings. For each ring, we calculated the magnetic force acting on the magnet. By summing these forces with the gravitational force, we computed the net force, which was then used to update the magnet's velocity and position as it moved through the tube. The computational model predicted a total time of 1.97 seconds, which was slightly longer than the experimental result. So, during the velocity versus time analysis, the velocity versus time graph from the computational model revealed key insights. At the beginning and end of the motion, magnetic and gravitational forces were unbalanced, causing changes in velocity. In the middle, the forces balanced out, resulting in constant velocity as the magnet moved through the tube. And the intensity of the coloring in the tube represented the magnitude of the current flowing through each ring. Using Lenz's law, we identified that the red indicated counterclockwise current when viewed from above, while blue indicated clockwise current. Some of the sources of error were identified. The primary source was inaccurate magnetic dipole moment measurement from a previous experiment, which affected the computational model. Other errors included the magnet possibly hitting the tube walls if it wasn't dropped straight, and human timing errors when recording the experimental results. To improve the accuracy of the computational model, we could divide the tube into more rings to increase resolution, conduct additional trials to reduce random errors, and recalculate the magnetic dipole moment for better precision. Now let's take a look at the what if questions. What if the resistivity of the conductor was minimized to nearly zero? This would result in a larger induced current, creating a stronger magnetic field and greater opposing force. The magnet would fall slower through the tube. And another thing, what if holes or slots were introduced to the tube? This would reduce the induced current, weaken the magnetic force, and cause the magnet to fall faster. And let's finally take a look at our conclusion. In conclusion, while there were some discrepancies between the experimental and computational models, both demonstrated that the magnet fell slower through the aluminum foil tube than it would in free space. This is due to the upward magnetic force generated by the induced current as explained by Faraday's law. This lab provided a practical real-world demonstration of Faraday's law and enhanced our understanding of this fundamental principle. Thank you for listening.